Our universe is a web of unimaginable scale, a tapestry woven from galaxies and galaxy clusters. Yet its story begins with a whisper of near-perfect uniformity. This is the central mystery of cosmic structure formation, the universe's greatest construction project. How did everything we see, from the smallest dwarf galaxy to the largest supercluster, build itself from almost nothing? By the end of this journey, you will understand how the grand architecture of the cosmos emerged from the faintest quantum ripples. The infant universe was astonishingly smooth, a featureless sea of energy. Today, it is a complex hierarchy of light and matter. What invisible blueprint guided this epic transformation, and what forces laid the first stones in the dark? When you look up at the night sky, what do you think it is truly made of? The evidence for this profound smoothness is written across the entire sky. It is called the cosmic microwave background, and it is the oldest light in the universe, a fossilized glow from a time when the cosmos was just 380,000 years old. When we map this ancient light with incredible precision, we find it is almost perfectly uniform. From one region of the sky to another, the temperature varies by only about 1 part in 100,000. To grasp that level of smoothness, picture a sheet of glass so flawless that its thickness varies by no more than the width of a single human hair over a distance of a football field. That was the infant universe, a vast, hot, and nearly featureless sea of plasma. When we say the universe began from nearly nothing, we do not mean empty space. We mean the absence of any obvious starting points, the lack of any grand density contrasts that could naturally collapse into galaxies. This primordial perfection is the ultimate cosmic blank slate, and it presents our deepest puzzle. If everything was so incredibly even, where did the blueprint for our cosmic web come from? A perfectly smooth universe would have remained smooth forever, a static ocean with no islands of matter. For construction to begin, the universe needed its first imperfections, the faintest of seeds scattered into that smooth sea. That faint 1 part in 100,000 variation in the cosmic microwave background is the entire story. Those tiny temperature differences are the universe's first whispers, the earliest signatures of density. A slightly warmer patch in that ancient light corresponds to a region where the primordial plasma was just a tiny bit denser and hotter. A slightly cooler patch marks a region that was ever so slightly more sparse. These are the primordial density fluctuations, the cosmic seeds from which every structure would eventually grow. Without them, gravity would have had nothing to work with. A perfectly uniform universe expands perfectly uniformly forever, a featureless and silent void. For islands of matter to form, you need the slightest gathering of material, a gravitational foothold. Think of it like a vast, calm lake. If the surface is perfectly smooth, it remains a flat mirror. But introduce the smallest ripple, a single raised droplet, and suddenly the water around it begins to flow. That droplet attracts more water, growing into a small wave which can then combine with others. In the cosmic lake, gravity is the force that pulls matter toward those initial ripples. An overdense region, however minuscule, exerts a slightly stronger gravitational pull than its surroundings. It begins to attract nearby matter, growing denser and more massive over time. Conversely, an underdense region, a cosmic valley, loses material to its denser neighbors, becoming even emptier. This is the fundamental engine of structure formation, a gravitational sorting of the cosmos that turns faint whispers into mighty shouts over billions of years. But this only pushes the mystery one step further back in time. We have found the seeds imprinted in the oldest light we can see. But where did the seeds themselves come from? What cosmic process, in the very first moments of existence, had the audacity to break that perfect symmetry and plant the blueprint for everything? To answer that, we must venture into a realm where physics meets philosophy, to a time so early that the universe was not just hot but fundamentally different. The answer lies in a concept so powerful it reshaped our understanding of the cosmos itself. This is cosmic inflation, a storm of exponential expansion in the very first fraction of a second after the beginning. Picture the universe not just expanding, but inflating like a balloon being blown up at an unimaginable rate, stretching by a factor of a trillion in a span of time so short it defies comprehension. During this inflationary epoch, the fabric of space itself was stretched smoother than any sheet of glass, ironing out any pre-existing wrinkles and creating that profound uniformity we see in the cosmic microwave background. But inflation did something even more remarkable. It took the faintest whispers of the quantum world and blew them up to cosmic proportions. At the tiniest scales, even what we call empty space is not truly empty. It is a seething sea of potential, where quantum fields exhibit tiny, random fluctuations. Energy flickers in and out of existence, particles and antiparticles popping up for fleeting moments before annihilating each other. These are quantum fluctuations inherent to the fabric of reality itself. Normally, these fluctuations are microscopic and transient, canceling themselves out almost instantly. But during the furious stretching of inflation, something extraordinary happened. Space expanded so rapidly that these tiny quantum ripples did not have time to smooth themselves out. Instead, they were stretched along with space itself, frozen into the fabric of the cosmos as minute differences in the density of energy. Think of it like drawing a tiny, intricate pattern on the surface of a deflated balloon. If you inflate that balloon to the size of a city, the pattern is magnified enormously, its details now writ large across a vast area. Inflation did exactly that to the quantum jitter. Those random flickers became the faint 1 part in 100,000 density variations, the primordial seeds imprinted across the entire universe. When inflation ended, its immense energy transformed into the hot soup of particles of the Big Bang plasma, and those frozen quantum ripples became the slight over densities and under densities in matter and energy. They were the universe's first and only blueprint. Every galaxy cluster, every filament of the cosmic web, every solitary galaxy orbiting in the dark can trace its origin back to those magnified quantum whispers from the first moment of time. This means the grandest structures we see today, the great walls of galaxies and vast cosmic voids, are fundamentally quantum mechanical in origin. It is a staggering connection between the smallest rules governing particles and the largest scales of the cosmos. So when you look up at the night sky, you are not just looking at distant points of light. You are witnessing the amplified echo of a quantum storm that raged when the universe was less than a trillionth of a second old. These quantum ripples stretched to cosmic scales are not just a theoretical idea. We can see their direct imprint today, frozen in time. That ancient light from the universe's infancy, the cosmic microwave background, is our ultimate photographic plate. When we look at it, we are not seeing galaxies or stars. We are seeing the moment those first density seeds became permanently etched into the fabric of reality. At an age of 380,000 years, the universe had finally cooled enough for atoms to form, allowing light to travel freely for the first time. That light, which has been traveling for over 13 billion years to reach our telescopes, carries a snapshot of exactly how matter was distributed at that pivotal moment. The pattern of slightly hotter and slightly colder spots across the entire sky is a one-to-one map of those primordial overdensities and underdensities. A hot spot is a region where matter was slightly more packed together. A cold spot marks a slightly emptier region. This is the universe's original blueprint, and we are holding it in our hands. But cosmologists do more than just admire this map. They decode it with mathematical precision, measuring the statistical properties of these spots to read the fine print of creation. They ask questions about the pattern itself. How many large spots are there compared to medium or small ones? How much does the temperature vary from one spot to the next? The answers form a unique fingerprint, a signature that tells us about the physics of the inflationary epoch that created the seeds. The predictions from inflationary theory are remarkably specific. They forecast a particular distribution of spot sizes and intensities, a kind of cosmic barcode that should be imprinted on the cosmic microwave background. When our most powerful space-based observatories, like the Planck satellite, took exquisitely detailed measurements of this ancient light, they found a near-perfect match. The observed statistical pattern aligns with the predictions of a simple inflationary model. This is one of the strongest validations in all of modern cosmology. It tells us that the story holds together, that the quantum origins of structure are not just a beautiful idea, but a description of what actually happened. Those faint temperature differences, mere millionths of a degree, are the confirmed starting conditions for everything that followed. They are the initial gravitational footholds from which, over billions of years, the first stars ignited, galaxies swirled, and the vast cosmic web slowly drew itself into existence. Yet this magnificent blueprint of light and matter is only half the story. If we took that cosmic microwave background map, those primordial seeds, and simulated a universe using only the ordinary matter we know and love, the atoms that make up stars and planets and you and me, something would go terribly wrong. The structures that would form would be far too small, far too faint, and far too slow to ever resemble the universe we actually observe. This is one of cosmology's great realizations, that the visible universe is merely the decorative finish on a framework built from something else entirely, something we cannot see. The cosmos required an invisible scaffolding, a hidden form of matter that does not shine, reflect, or interact with light in any way. We call it dark matter, and without it, galaxies as we know them could not exist. To understand why, we need to revisit that hot, dense plasma of the early universe. For its first few 100,000 years, ordinary matter, which scientists call baryonic matter, was not free to simply fall into those gravitational wells created by the density seeds. It was tightly coupled to light, to radiation. Photons of light were constantly bouncing off the charged particles, protons and electrons, creating an intense pressure that resisted gravity's pull. Imagine trying to build a sandcastle underwater. Every time you try to pile sand into a mound, the water's pressure and currents push it back, smoothing it out. For ordinary matter in that primordial soup, radiation pressure was that relentless current, preventing it from clumping together effectively. The seeds were there, but the building material was too slippery, too energetic to settle into them quickly. Dark matter solves this problem with an almost elegant simplicity. We believe it is cold, meaning its particles move relatively slowly, and crucially, it does not interact with light or radiation at all. It is, for all intents and purposes, invisible to everything except gravity. This changes everything. While ordinary matter was struggling against the photon pressure, dark matter felt only the gentle, persistent tug of gravity. From the very instant after inflation, those quantum ripples created gravitational potentials, subtle dips in the fabric of space-time. The cold, dark matter particles, unaffected by the cosmic traffic jam of light, could immediately begin to slide into these dips. They started gathering slowly and silently, millions of years before the universe became transparent. These gatherings of dark matter became the first gravitational anchors in the cosmos. They formed vast, diffuse, invisible clouds called dark matter halos. Think of these halos as the foundational molds or frameworks for future structure. They grew hierarchically, with smaller halos merging to form larger ones, weaving the first threads of the cosmic web in the utter dark. Only later, when the universe had cooled enough for atoms to form and light to travel freely, did ordinary matter finally break free from the grip of radiation. By then, it found itself in a universe already sculpted by gravity. The baryonic matter, the gas that would become stars and galaxies, flowed along the gravitational contours already established by the dark matter. It cascaded into the deep wells of those pre-existing dark matter halos, where it could cool, condense, and eventually ignite into the first brilliant points of light. So when we look at a majestic spiral galaxy today, we are not seeing its true form. We are seeing the luminous tracer of something far more massive and extensive. The stars and gas we observe are like the lights of a city seen from an airplane at night, outlining the shape of the land beneath. The city itself, the continent of dark matter that defines the galaxy's gravity and holds it together, remains shrouded in darkness. This invisible skeleton comprises over 5 times more mass than all the visible matter combined. It is the hidden architecture that dictated where galaxies would form, how they would cluster, and how the great walls and filaments of the cosmic web took shape. The story of cosmic structure, therefore, is a duet between the quantum seeds imprinted by inflation and the gravitational choreography conducted by dark matter. One provided the pattern and the other provided the means to build it, but this raises a profound and unsettling question. If dark matter is the dominant gravitational force in the universe, shaping everything from the largest clusters to the smallest dwarf galaxies, then what in the world is it actually made of? The universe had its blueprint, and now it had its builder. In the profound darkness following inflation, the stage was set for the first act of cosmic construction. Driven solely by the relentless pull of gravity, the faint overdensities imprinted by those quantum ripples began their slow, transformative work. Picture the fabric of the early universe not as a flat sheet, but as a gently wrinkled landscape, its subtle hills and valleys defined by those 1 part in 100,000 differences in density. In this landscape, the mysterious, cold dark matter acted like a fine mist settling across the terrain. Gravity, the universe's great leveler, began to pull this invisible material. The mist began to flow almost imperceptibly at first from the cosmic hills down into the valleys. Where the density was slightly higher, the gravitational pull was slightly stronger, attracting more dark matter. This made the region even denser, which increased its pull further in a powerful feedback loop known as gravitational collapse. Over hundreds of millions of years, this process sculpted the dark matter into a vast, interconnected network. The densest valleys grew into massive, spherical clouds called dark matter halos. The ridges between them stretched into long, tenuous threads, forming a cosmic web of filaments. This was the universe's hidden skeleton, its true infrastructure, taking shape long before the first star ever flickered. The halos themselves were not solid objects, but rather diffuse, swirling clouds of invisible particles held together by their own gravity. They grew hierarchically, with smaller halos merging together to form larger and larger ones like droplets of mercury coalescing. Each of these halos created a deep gravitational well, a pit in the fabric of spacetime. Think of a bowling ball placed on a taut rubber sheet, creating a deep depression. Any object rolling nearby would naturally spiral down into that depression. These dark matter halos were the universe's first and most massive gravitational bowling balls. They established the locations where everything luminous would eventually be drawn. The ordinary gas, the baryonic matter that had been buffeted by radiation pressure, now found itself in a universe already pre-structured by this invisible gravity. Once the universe cooled and became transparent, that gas was free to move, and it flowed directly into the deep, waiting potentials carved out by the dark matter. The framework was complete. Every galaxy, every cluster we see today is not where it is by accident. It sits at the nexus of this ancient, dark architecture, a luminous ornament on a scaffold we are only beginning to map. After the cosmic microwave background faded into the infrared, the universe entered its longest and quietest night. For nearly 100 million years, a profound and unbroken darkness settled over the cosmos. This era is known as the Cosmic Dark Ages, and it was a universe utterly alien to our own. No stars pierced the gloom, no galaxies swirled in the void. The only light was the faint, cooling afterglow of the Big Bang itself, stretched now into invisibility. All that existed was a vast, featureless fog of neutral hydrogen and helium gas, a simple sea of atoms drifting through an expanding, lightless space. Yet in that perfect dark, the silent work of construction never ceased. The invisible architecture of dark matter, now fully established as a cosmic web of halos and filaments, continued its relentless growth. Unseen and unfelt by the neutral gas, these gravitational wells deepened, their pull strengthening as more dark matter streamed in. The gas itself, though neutral and dark, was not immune to this influence. Each atom of hydrogen and helium, while oblivious to the light that had once pushed it around, could still feel the persistent tug of gravity, and so, across the cosmos, an imperceptible migration began. The primordial gas, spread almost perfectly evenly, started a slow cosmic drift. It began to seep toward the regions of strongest gravity, flowing along the invisible contours of the dark matter framework. Imagine a fine, dark powder scattered across an intricate, three-dimensional mold. You cannot see the mold itself, but as a gentle vibration shakes the powder, it gradually settles into every groove and hollow, revealing the shape hidden beneath. In the Dark Ages, gravity was that gentle, universal vibration. The neutral gas was the powder, and as it drifted, it started to outline the ghostly skeleton of dark matter. Vast reservoirs of gas pooled at the centers of the largest dark matter halos. These clouds grew denser and denser, their internal pressure and heat beginning to build. For millions of years, nothing seemed to happen. The gas simply gathered, compressing in the absolute cold and dark. But this was the essential, quiet preparation. Every gathering cloud was a cosmic furnace being stacked with fuel, a birthplace being readied. The universe was holding its breath, waiting in the dark for the spark that would end the long night and ignite the first chapter of light. That first spark did not come from a match, but from a crushing, cosmic embrace. Deep within the largest of those dark matter halos, vast clouds of hydrogen and helium gas had been gathering for tens of millions of years. As more and more gas pooled at the center, drawn in by the halo's immense gravity, the pressure at the core became unimaginable. The gas grew hotter and denser, a seething, chaotic mass with nowhere left to go. Finally, it reached a tipping point. The outward push of heat and pressure could no longer resist the inward crush of gravity. The core collapsed catastrophically. In that moment of supreme compression, the universe crossed a threshold it had never crossed before. The temperatures at the heart of that collapsing cloud soared to over 10 million degrees. At that critical heat, the protons of hydrogen nuclei, which normally repel each other with fierce electrical force, were slammed together with enough violence to overcome their natural aversion. They fused, creating helium and releasing a torrent of pure energy in the process. Nuclear fusion, the engine of all stars, had been ignited for the very first time. A pinpoint of thermonuclear fire blazed into existence in the endless dark. The cosmic dark ages were over. This was not just any star. Astronomers call these first celestial furnaces population 3 stars, and they were unlike anything that exists today. Born from the pristine, unmixed clouds of only hydrogen and helium, with no heavier elements to help them cool and fragment, they likely grew to staggering sizes. Theories suggest they could have been hundreds of times more massive than our own sun, true cosmic behemoths. their brilliance would have been ferocious, pouring out ultraviolet light with an intensity that dwarfed modern stars. But such a furious life could not last. Burning their fuel at a prodigious rate, these titans lived fast and died young, likely surviving for only a few million years before meeting violent ends. Their deaths, however, were just as important as their births. In their spectacular final acts as supernova, these first stars would forge and scatter the universe's first heavy elements: carbon, oxygen, silicon, iron, seeding the primordial gas with the very ingredients necessary for rocky planets and ultimately life. That first generation of starlight did more than just illuminate the void. It began a fundamental transformation of the cosmos itself. The intense ultraviolet radiation from these massive stars ripped electrons from the atoms of the surrounding hydrogen gas, reionizing it and clearing away the fog that had permeated the dark ages. The universe became transparent again on a grand scale, but this time it was filled with new, local sources of light. Where once there was only a dark framework of matter, now brilliant beacons flickered on, one by one, tracing out the invisible architecture. The dark matter skeleton had finally been outlined in fire. This was the dawn of the cosmic dawn, the moment the universe began its long journey from a simple, dark sea of particles to the complex, luminous tapestry we are part of today. Yet these first stars were solitary giants in immense halos. How did their legacy lead to the crowded cities of stars we call galaxies? The brilliant deaths of those first stars were not an ending but a cosmic alarm clock. Their ferocious ultraviolet light began to flood the surrounding darkness, and this radiation did something profound to the fabric of the universe itself. For 100 million years, space had been filled with a cold fog of neutral hydrogen gas, where each atom's single electron was peacefully bound to its proton. The starlight from these new, massive objects was so energetic it acted like a universal solvent. Photon by photon, it blasted into those hydrogen atoms, stripping the electrons away in a process we call reionization. Think of it like a great thaw across the cosmos. Where once there was an opaque frost of neutral atoms, the intense starlight began to clear windows, creating vast, transparent bubbles of hot, ionized plasma, gas where electrons and nuclei were separated and free. This was the universe's great awakening. For the second time in its history, light could travel freely across vast distances, but now it was not the uniform glow of the Big Bang's aftermath. It was the specific, localized light of individual stars and the fledgling collections that would become the first galaxies. Reionization did not happen everywhere at once. It was a patchwork process unfolding over hundreds of millions of years. The most active regions where massive stars were being born in dense clusters became brilliant, expanding bubbles of transparency. These bubbles eventually grew, overlapped, and merged until the entire intergalactic medium was once again ionized. This transformation fundamentally changed the rules for everything that came after. The neutral hydrogen fog that had once helped gas clouds cool and collapse was now gone. The universe was now filled with a thin, hot, ionized plasma, a more hostile environment for the birth of future galaxies. Only within the protective depths of large dark matter halos, where gas was dense enough to shield itself, could new stars continue to form. Reionization, therefore, acted as a kind of cosmic filter. It suppressed the formation of small, faint galaxies in the emptier regions while allowing the giants in the densest nodes to thrive, further shaping the hierarchy of the cosmic web we see today. We can still detect the echoes of this epic transition. The most distant quasars, brilliant beacons from the early universe, show us a telltale signature. Their light, traveling for over 13 billion years, carries the faint absorption lines of the last remaining patches of neutral hydrogen, like shadows on the wall of a newly lit room. This allows us to pinpoint the era when the final bubbles merged and the cosmic dawn was complete, a permanent and pivotal shift in the character of the cosmos. But the silent, invisible framework of dark matter was only half of the story. For the universe to build the luminous structures we see, it needed to work with a far more temperamental material, ordinary matter, or what cosmologists call baryons. While dark matter simply clumped under gravity's straightforward pull, baryonic matter, the gas of hydrogen and helium, behaved in a spectacularly complex and messy way. This is where the simple blueprint met the chaotic reality of physics, and where the true diversity of the cosmos was born. Think of dark matter as the steel frame of a skyscraper, predictable and strong, defining the overall shape. The baryonic gas is like all the materials that go inside, the concrete, wiring, and glass. But this material is alive, reacting to heat, radiating energy, and swirling with internal motion. Its behavior determines whether the building becomes a dense, brilliant tower of light or remains a dark, empty shell. The first and most critical process for any forming galaxy is gas cooling. When gas falls into a dark matter halo, it gains gravitational energy, which makes it heat up, just like air heats up when you compress it in a bicycle pump. A hot, high-pressure cloud will resist collapsing further. It will simply bounce and swirl. For stars to form, that gas must shed this heat. It must cool down and condense into dense, cold clumps. Luckily, atoms are excellent at this. When atoms collide, they can excite their electrons, and those electrons later release that energy as photons of light, radiating the heat away into space. It is a cosmic air conditioning system. Hydrogen atoms, especially, can cool very efficiently by radiating in specific wavelengths. This cooling allows the gas to settle into a rotating disk at the center of the halo, losing its turbulent energy and becoming quiet enough for gravity to finally win. But cooling is not the only force at play. As soon as the first stars ignite, they begin a violent counterattack against gravity. These stars flood their surroundings with intense ultraviolet radiation, heating the gas back up. And when the most massive stars die in supernova explosions, they unleash titanic shockwaves, blasting gas out of the halo entirely or reheating it to millions of degrees. This creates a fierce feedback loop. Star formation tries to cool and condense gas, but the stars themselves, through their radiation and explosive deaths, work to heat it up and blow it away. The fate of a galaxy hinges on this delicate balance. Other factors come into the mix. The gas itself has pressure, which acts as a cushion against collapse. It also carries angular momentum from the swirling motion of the cosmic web, causing it to spin faster as it falls inward, much like an ice skater pulling in their arms. This spin can prevent a single, monolithic collapse, instead favoring the formation of a flattened, rotating disk. All of these processes, cooling, heating, pressure, and spin, are the messy details of baryonic physics. This complexity is the ultimate answer to a beautiful mystery. Dark matter halos of similar size and mass formed all across the early universe, following the same simple gravitational rules. Yet from these nearly identical foundations, we see a staggering variety of galaxies, from tiny, faint dwarfs to majestic spirals and giant, red ellipticals. The difference lies entirely in how the baryonic gas behaved within each halo. In one halo, the gas may have cooled slowly and steadily, forming stars in an orderly rotation, giving birth to a spiral galaxy like our Milky Way. In another, perhaps two massive halos merged. Their gas clouds collided violently, shocking and heating the gas so much that it could not cool quickly, preventing disk formation and instead creating a giant, smooth, football-shaped elliptical galaxy where new star formation was effectively shut down. In a small halo, a single, powerful supernova might have blown away almost all of the gas, leaving behind only a dark matter skeleton with a few scattered stars, a failed dwarf galaxy. So when we admire the different shapes in a gallery of galaxies, we are not just looking at different arrangements of stars. We are witnessing the unique historical record of a cosmic battle, a billion-year struggle between the relentless pull of gravity and the turbulent, energetic, and often self-destructive nature of ordinary matter. The dark matter provided the theater, but the baryonic gas wrote the dramatic and wildly varied script. The universe's construction project followed a remarkably simple, yet powerful, rule. Everything grew from the bottom up. This is the principle of hierarchical clustering, and it is the dominant story of how our cosmic web assembled itself. Those initial quantum seeds did not blossom into a fully formed supercluster overnight. Instead, gravity worked patiently, starting with the smallest possible units and letting them combine, step by step, into the giants we see today. The first dark matter halos to condense from the smooth early universe were tiny, perhaps no more massive than a small mountain here on Earth. They were the cosmic equivalent of pebbles. But gravity is an irresistible social force. These small halos, drawn together by their mutual attraction, began to merge. Two pebbles would come together to form a stone, several stones would combine into a boulder, and boulders would gather into vast celestial mountains. This process never truly stopped. It is a continuous cascade of consolidation, a cosmic assembly line where the product of one merger becomes the raw material for the next. Dwarf galaxies, the smallest collections of stars, merge to build larger galaxies like our Milky Way. Those galaxies, in turn, were drawn into groups, and those groups collided and merged to form immense galaxy clusters, the largest gravitationally bound structures in existence. Even clusters are not the end, as they themselves are pulled into sprawling superclusters. Though these are so vast, they are still being stretched by the expansion of the universe itself. Think of it like the watershed of a continent. The first rain creates tiny trickles in the soil. Those trickles merge into streams, streams converge into rivers, and mighty rivers finally flow together into the ocean. The cosmic web is that watershed, with gravity as the relentless pull downhill, guiding every fragment of matter into ever larger congregations. We are not just theorizing this bottom-up growth, we can see it happening. Look at any deep image of the universe, and you will find galaxies with bizarre, distorted shapes, long tidal tails of stars stretching into space, or double nuclei at their hearts. These are the cosmic crime scenes, the evidence of recent mergers. A serene spiral galaxy showing signs of a violent disruption tells us we are catching it in the act of digesting a smaller neighbor. The Milky Way itself bears the scars of this history, with streams of stars in its halo that are the remnants of dwarf galaxies it consumed billions of years ago. This elegant, bottom-up process solves a profound puzzle. It explains how a universe that started with only microscopic density variations could, through the relentless and patient work of gravity, build a hierarchy of structure of such breathtaking scale and complexity. From quantum pebbles to galactic mountains, the story is one of endless combination. But if gravity is constantly pulling things together, why hasn't everything just collapsed into one unimaginably dense point? What counterforce keeps the cosmic construction site from imploding under its own weight? Gravity's relentless pull toward collapse is counterbalanced by a force of unimaginable fury, a final architect waiting in the dark heart of every growing city of stars. As galaxies matured through mergers and feasted on cosmic gas, a new and dominant player awoke, one that would ultimately decide their final size and shape. This architect is the supermassive black hole, lurking at the center of nearly every large galaxy, including our own Milky Way. These cosmic monsters contain the mass of millions or even billions of suns compressed into a point of infinite density. For most of their existence, they are quiet, dormant beasts. But when a galaxy's merger or a steady flow of gas drives fresh material too close, the black hole begins to feed. As matter spirals inward at nearly the speed of light, it forms a swirling, superheated disk of plasma, an accretion disk brighter than all the stars in the galaxy combined. This transforms the quiet black hole into an active galactic nucleus, or AN, one of the most energetic phenomena in the universe. We see them across the cosmos as brilliant quasars, their light outshining entire galaxies from billions of light years away. But this brilliance is not just a spectacle, it is a tool. The energy pouring from an active black hole does something extraordinary. It acts as a universal regulator. The intense radiation and powerful magnetic fields can drive colossal winds of hot gas, blasting outward at thousands of kilometers per second. These winds scour the galaxy's central regions, heating the surrounding gas reservoir to such extreme temperatures that it cannot cool down and collapse to form new stars. Think of it as a cosmic furnace with a safety valve. As the galaxy feeds gas to its central black hole, the black hole responds by turning up the heat, violently preventing the galaxy from consuming all its fuel too quickly. This process, called AGN feedback, is a crucial late-stage check on growth. Without it, the largest galaxies would gorge themselves on gas, forming stars in a frantic rush until they exhausted everything, leaving behind a bloated, lifeless giant. The black hole's furious output prevents this overconsumption. It effectively puts the galaxy on a diet, limiting how many new stars it can create and ultimately determining its final luminosity and size. We see evidence of this balancing act everywhere. The most massive, red, elliptical galaxies, where star formation has long since ceased, almost always harbor supermassive black holes whose masses are precisely proportional to the mass of the galaxy's central bulge. This tight correlation is no accident. It is the signature of a billion-year-long dialogue between the galaxy and its dark heart. The black hole grew as the galaxy grew, and its final, explosive feedback phases shut down the very process that fed it. So when we look at the quiet, mature galaxies in our modern universe, we are seeing the end result of this self-regulating cycle. The most powerful forces of construction, gravity, and star formation were ultimately tempered by the most powerful force of destruction, a black hole's rage, to create the stable cosmic landscape we inherit today. The narrative we have woven, from quantum whispers to galactic empires, is elegant and compelling. But is it true? How can we possibly test a story that spans nearly 14 billion years and involves forces we cannot directly see? The answer lies not in a laboratory, but in a universe of pure mathematics, built inside the world's most powerful supercomputers. This is the realm of cosmological simulation, where theorists become cosmic architects, programming the laws of physics to see if they can build a virtual cosmos that mirrors our own. The most ambitious of these projects, with names like Illustris, Millennium, and Eagle, are among the largest and most complex calculations ever undertaken. They begin with a digital blank slate, a virtual volume of space representing a cube billions of light years across. Into this volume, they imprint the exact same initial conditions we observe in the cosmic microwave background, that faint 1 part in 100,000 pattern of density ripples. They then populate this space with particles representing dark matter and gas. The final, crucial step is to tell these particles how to behave. The simulation codes in the fundamental laws, the gravity that pulls dark matter into halos, the hydrodynamics that govern how gas swirls, cools, and heats, the recipes for turning cold, dense gas into virtual stars, and even the explosive feedback from supernova and supermassive black holes. With everything set, they press start, and the simulation runs forward in time, compressing billions of years of cosmic evolution into months of raw computation. As the virtual clock ticks, gravity goes to work. The dark matter weaves itself into a vast cosmic web of filaments and halos, just as our theories predict. Then the gas follows, flowing into those halos, cooling, fragmenting, and igniting into populations of virtual stars. Galaxies are born, they merge, they spin, they evolve. Black holes form at their centers and occasionally erupt, blasting energy back into their surroundings. The simulation does not know what a galaxy should look like, it only knows the rules. So what happens when we step back and look at the final result? This fully evolved digital universe, the validation is breathtaking. When astronomers compare these simulations to our deepest maps of the real cosmos, the agreement is staggering. The large-scale distribution of galaxies, the intricate filaments and vast voids of the cosmic web, the statistical properties of galaxy clusters, all emerge naturally from the code. The simulations produce grand spiral galaxies and smooth elliptical giants in roughly the right proportions. They even recreate the observed relationship between a galaxy's mass and the mass of the black hole at its heart. It is a profound confirmation. We are not just telling a good story, we are writing the equations of that story into a computer and watching it spontaneously generate a reasonable copy of our observable universe. This does not mean every detail is perfect. The messy physics of star formation and black hole feedback remain areas of active tuning. But the fact that the broad architecture of the cosmos emerges at all from such simple starting conditions is a triumph of modern cosmology. These virtual universes tell us our fundamental understanding is sound, that gravity, dark matter, and the standard model of physics can indeed build a world that looks remarkably like home. Zooming out to the grandest possible scale, the universe reveals its final form. It is not a random scatter of galaxies like dust tossed into the void. Instead, it is a magnificent, intricate architecture, a vast cosmic web. This web is a tapestry woven from brilliant filaments of galaxies, great walls, and dense clusters, all surrounding incomprehensibly empty regions known as cosmic voids. This is the largest pattern in existence, the ultimate structure built from almost nothing. If you could view the cosmos from a godlike perspective, you would see a sponge-like structure, a luminous foam where the galaxies trace out the dense ridges and the voids are the empty bubbles within. This is not an artist's impression, it is the direct result of the gravitational story we have been following. Those initial dark matter halos formed from the quantum seeds were never isolated. They were born along the intersections and strands of a faint, three-dimensional network that permeated the entire early universe. As gravity worked over billions of years, it did not just pull matter into isolated points, it drew it along these pre-existing lines of strength. Think of water condensing on a spider's web. The droplets do not form randomly, they gather along the silken threads, growing larger where the threads intersect. In the cosmic web, dark matter was the invisible silk, and galaxies are the luminous droplets. The gas that formed stars and galaxies simply followed this underlying dark matter skeleton, flowing along the filaments and pooling at the nodes where filaments crossed. These nodes became the universe's great cities, the massive galaxy clusters containing thousands of galaxies. The filaments themselves became the great highways connecting these metropolitan centers, long chains of galaxies stretching for hundreds of millions of light years. And the voids, those vast empty regions, are the natural outcome of this gravitational sorting. As matter drained into the web, it left behind these immense, ever-expanding deserts of near-nothingness. We can see this structure directly. Projects like the Sloan Digital Sky Survey have painstakingly mapped the positions of millions of galaxies, and when we plot them in 3 dimensions, the web emerges with stunning clarity. It is a map of the universe's growth, a fossil record of gravity's patient work. The Great Walls, like the Sloan Great Wall, are not solid barriers but dense sheets of galaxies, the intersections of multiple filaments. This cosmic architecture is the final, majestic expression of a process that began with quantum ripples smaller than a single atom. From those microscopic imperfections, gravity built continents of galaxies, a web of light spun across the darkness. At the densest intersections of the cosmic web, gravity has built its ultimate masterpieces. These are galaxy clusters, the largest structures in the universe that are held together by their own gravity. While superclusters are even larger, they are still being stretched apart by cosmic expansion. A true galaxy cluster is a self-contained metropolis, a colossal island of matter that has fully collapsed under its own immense weight. Within a volume of space just a few million light-years across, you will find not just one galaxy, but hundreds, even thousands of them, all orbiting a common center. They are a mix of majestic spirals and giant, red elliptical galaxies, swarming like bees in a hive, but the galaxies themselves are merely the visible streetlights of this cosmic city. They account for less than 5% of the cluster's total mass. The true bulk of a cluster is found in two invisible components. First, there is an enormous reservoir of dark matter, whose gravitational pull is the mortar holding the entire structure together. Second, there is a vast, thin atmosphere of superheated gas that fills the space between the galaxies. This gas is not cold and dark. It is a seething plasma at temperatures of tens of millions of degrees, so hot that it glows not in visible light, but in powerful X-rays. In fact, when we point X-ray telescopes at a cluster, we see it not as a collection of points, but as a giant, fuzzy ball of luminous energy, a cosmic furnace that contains more ordinary matter than all the galaxies within it combined. This hot gas is a direct record of the cluster's violent formation. As matter cascaded down the filaments of the cosmic web and crashed together at the intersection, the gas was compressed and shocked to these incredible temperatures. The cluster's immense gravity holds onto this seething atmosphere, preventing it from simply flying away. This entire system, the swarm of galaxies, the X-ray gas, and the dominant dark matter halo, forms a single, gravitationally bound entity. It is the endpoint of the hierarchical merging process, the final destination for matter flowing along the Webb's great highways. Because they represent the most massive collapsed objects in existence, galaxy clusters are extraordinary cosmic laboratories. Their sheer abundance and properties serve as a critical test for our entire understanding of cosmology and structure formation. Think of it this way: if our models of dark matter, gravity, and the initial seeds from inflation are correct, they should predict a certain number of clusters of a given mass at different points in the universe's history. Finding too many or too few massive clusters would mean something in our fundamental recipe is wrong. By surveying the sky and weighing these giants, often by measuring how their gravity bends light from more distant galaxies, we take the universe's temperature. We ask, does the story we have told, from quantum ripples to dark matter scaffolding, actually produce the distribution of the largest structures we observe? The answer so far is a remarkable yes. The clusters we find match the predictions, offering powerful confirmation that our cosmic narrative is on the right track. They stand as the final monuments to gravity's patient, billion-year construction project. Yet for all the brilliance of clusters and filaments, most of the universe is not there at all. If the cosmic web is a magnificent sponge, then the vast majority of its volume is made of the holes. These are the cosmic voids, the great empty spaces that stretch between the luminous threads of the web, spanning tens to hundreds of millions of light-years across. They are the other side of the cosmic coin, the natural and necessary consequence of how gravity sculpted the cosmos. Remember those initial quantum ripples, the faint overdensities and underdensities. While gravity pulled matter into the overdensities, weaving the filaments and clusters, it was simultaneously draining matter out of the underdensities. Voids are those initial underdense regions, amplified over billions of years. As matter flowed toward the growing web, it left behind ever-expanding deserts of near-nothingness. Think of a growing city. As people move into the metropolitan center, the surrounding countryside empties out. On a cosmic scale, the voids are that emptying countryside, regions where the density of galaxies can be 100 times lower than in the filaments. They are not completely empty, of course. A typical void might still contain a few isolated, lonely galaxies and a very thin mist of hydrogen gas. But compared to the bustling galactic cities, they are profoundly quiet and dark, occupying most of the total volume of the observable universe. Their existence is a direct prediction of our model. If the initial seeds had only overdensities, we would not see such a clean, web-like pattern. It is the interplay between the dense ridges and the empty valleys that gives the cosmos its spongy architecture. Voids are not passive background, however. Their geometry and evolution hold unique secrets about the universe's contents and fate. Because they are vast, low-density regions, they are particularly sensitive to the effects of dark energy, the mysterious force accelerating cosmic expansion. Within a dense cluster, gravity's pull is so strong it dominates local dynamics, holding the structure together against the overall expansion. But inside a void where gravity's grip is extremely weak, the repulsive push of dark energy has a more pronounced effect. The void itself expands faster than the universe on average. By carefully mapping the shapes and growth rates of these cosmic bubbles over time, astronomers can place tight constraints on the nature of dark energy itself. The voids, in their immense silence, become a novel laboratory for probing the universe's most elusive component. So when we map the grand structure of everything, we must look not only at where the light is, but also at where it is not. The great emptiness is as much a part of the story as the brilliant clusters, two sides of a single sheet of paper, first crumpled by quantum hands nearly 14 billion years ago. Our elegant cosmic model, however, faces a serious and intriguing challenge right here in our own galactic neighborhood. The most sophisticated simulations of how a galaxy like the Milky Way should form tell a very specific story. They predict that our galaxy should be surrounded by a vast swarm of small satellite galaxies, perhaps hundreds of them, each tracing the orbit of its own small dark matter halo. Yet when we look up, we count only a few dozen. This glaring mismatch between prediction and observation is known as the missing satellites problem. Where are all those small galaxies that our theories insist should be there? It is not that the simulations are fundamentally wrong. They beautifully reproduce the large-scale cosmic web. The issue seems to lie in the messy transition from dark matter halo to luminous galaxy, especially for the smallest systems. One compelling solution suggests that the tiniest dark matter halos, those with the weakest gravity, faced an impossible challenge. When the first stars ignited across the universe and began the epoch of reionization, their intense ultraviolet radiation heated the cosmic gas to immense temperatures. In these smallest halos, gravity's grip was simply too feeble to hold onto that hot gas. The gas was evaporated away, stripped before it could ever cool and collapse into stars. These halos would have remained completely dark, invisible islands of pure dark matter drifting silently around the Milky Way. Another possibility involves the violence of early star formation itself. In a small halo that did manage to form a first generation of stars, even a single supernova explosion could be catastrophically powerful. The blast could blow all the remaining gas completely out of the tiny halo, shutting down any future star formation and leaving behind only a faint, ancient stellar population or perhaps nothing visible at all. Astronomers now search for the ghosts of these failed systems, ultra-faint dwarf galaxies with so few stars they are barely detectable, or streams of stars torn from them during mergers. The missing satellites problem does not break our model, it refines it. It forces us to better understand the complex astrophysics that determines whether a dark matter halo becomes a brilliant galaxy or remains a shadow in the dark. But the puzzles are not confined to the number of small galaxies, they extend to their very hearts. The internal structure of a dark matter halo, according to the clean, gravity-only simulations, should follow a predictable profile. Its density should rise steeply and smoothly toward the center, forming what cosmologists call a cusp. Picture a very smooth, steep hill, where the ground gets consistently denser the closer you walk to the summit. This cuspy profile is a direct prediction of how cold, collisionless dark matter should behave under gravity alone, with nothing to disrupt its smooth accumulation. Yet when astronomers study the motions of stars and gas within real dwarf galaxies, the faintest and smallest systems, they find something puzzling. The data often suggests the dark matter density is not a steep cusp at all, but instead remains nearly constant toward the center, forming a flatter, shallower core. It is as if the center of that dark matter hill has been scooped out and filled in, creating a small, flat plateau. This mismatch between the predicted cusp and the observed core is known as the Cusp-Core Problem, and it is one of the most persistent small-scale challenges to our standard model. How could the invisible dark matter, which supposedly only feels gravity, be rearranged from the inside? The leading solutions point to a remarkable and intricate conversation between the dark and the luminous universe. While dark matter may not interact with light, it is still subject to gravity, and the gravity in a small galaxy can be dramatically altered by the most violent events in its stellar population. Imagine a small, early dwarf galaxy. Its first generation of massive stars live short, furious lives and die in colossal supernova explosions. These are not gentle events. They release as much energy in an instant as the Sun will over its entire 10 billion-year lifetime. This energy does not just blow away gas, it creates powerful shockwaves that slam through the entire galactic center. This sudden, explosive injection of energy can cause the gravitational potential at the galaxy's heart to rapidly fluctuate. Think of it like shaking a bowl full of marbles. If you shake it vigorously, the marbles will not stay piled in a steep mound in the center. They will spread out, creating a shallower, more uniform distribution. In the galactic context, the supernova are the shaking, and the dark matter particles are the marbles. Through a process known as dynamical friction, the churning, moving gas from these repeated explosions can actually transfer energy to the dark matter, pushing it outward and smoothing the central cusp into a flatter core. This is not a minor tweak. It is a fundamental feedback mechanism where the explosive astrophysics of ordinary matter reaches back and sculpts the invisible dark matter skeleton that birthed it. The Cusp-Core Problem, therefore, is not a sign that dark matter is wrong, but rather a clue that the universe is more interconnected than we ever imagined. It suggests that to truly understand the dark, we must first master the brilliant, chaotic, and self-destructive drama of the stars. These subtle imprints on the cosmic web are not the only fossils left behind by the early universe. There is another, more geometric echo, a whisper from a time when the cosmos was not just hot, but ringing like a bell. This echo is frozen into the very distribution of galaxies we see today, and it provides us with a cosmic ruler of astonishing precision. Before the universe became transparent, before the cosmic microwave background was released, it was a seething, opaque fluid of plasma. In this dense medium, physics played out a dramatic tug of war. Gravity, constantly trying to pull matter together into denser clumps, was countered by the intense radiation pressure from the sea of photons. This competition created sound waves, but not sound as we know it. These were true pressure waves, mammoth compressions and rarefactions rippling through the entire cosmic fluid at over half the speed of light. Imagine dropping a stone into a still pond. The impact sends out circular ripples across the surface. In the primordial plasma, every one of those initial density seeds from inflation acted like a stone dropped into the cosmic pond. Each one generated a spherical pressure wave that expanded outward. For nearly 400,000 years, these waves surged through the hot soup, carrying shells of slightly denser matter with them. Then the music stopped when the universe cooled enough for atoms to form and the plasma cleared, becoming neutral. The photons suddenly stopped pushing. The radiation pressure vanished. At that precise moment, the sound waves froze in place. The outgoing shells of denser material were left stranded, like a wave frozen in mid-crash, imprinting a distinct scale onto the distribution of matter. That scale, the distance the sound wave could travel before the universe became neutral, is about 500 million light-years. It is known as the sound horizon, and it became a permanent stamp on the cosmos. This fossilized imprint is what we call a Baryon acoustic oscillation, or BAO. It is not a single object you can point a telescope at. Instead, it is a statistical preference woven into the fabric of the cosmic web. If you could take a census of millions of galaxies and measure the distances between every possible pair, you would find a curious signal. There is a slight excess of galaxy pairs separated by that magic distance of 500 million light-years. It is as if, on average, galaxies show a subtle tendency to be spaced one fossilized sound wave apart. This happens because those frozen shells of matter from the early waves were the preferred locations where galaxies would later form. They were the overdensities that gravity would later amplify. So when we map the universe in 3 dimensions, this preferred separation emerges as a faint but detectable pattern in the clustering of galaxies. For cosmologists, this is a gift of immense value. That 500 million light-year scale acts as a standard ruler etched into the sky. We know its true size from our understanding of the early universe's physics. When we look out at distant galaxies, we can measure how large this ruler appears to be from our vantage point. If the universe has expanded in a simple, predictable way, the ruler will appear a certain size. If the expansion has accelerated or changed, the apparent size will be different. By measuring this at different cosmic distances, we can trace the history of the universe's expansion with remarkable accuracy. It is like finding a series of identical yardsticks left at different depths in a stretching rubber sheet, allowing us to measure exactly how much the sheet has stretched between each one. Major galaxy surveys, like the Sloan Digital Sky Survey, have used this BAO signal to map the large-scale structure with unprecedented detail, confirming our model of cosmic evolution and placing tight constraints on the nature of dark energy. That frozen sound from the infancy of everything has become one of our most reliable guides to the fate of the cosmos. While gravity spent billions of years meticulously assembling the cosmic web, a new and opposing force was silently gaining strength. This is dark energy, the dominant component of our modern universe, and the mysterious agent responsible for its accelerating expansion. Unlike gravity, which pulls matter together, dark energy appears to be a property of empty space itself, exerting a gentle but relentless repulsive pressure that pushes the cosmos apart. For the first 9 billion years of cosmic history, gravity held the upper hand in this cosmic tug-of-war. The density of matter was high enough that its collective gravitational pull was slowing the universe's expansion, allowing structures to form and merge. But as the universe expanded, matter thinned out, diluting gravity's influence. Meanwhile, the repulsive push from dark energy, tied to the fabric of space, remained constant or even grew stronger as more space came into existence. Roughly 5 billion years ago, a cosmic milestone was reached. The density of dark energy surpassed the density of matter. From that moment forward, the expansion of the universe began to accelerate. This shift did not just change the rate of growth, it fundamentally altered the future of cosmic construction. Think of a master builder trying to assemble a vast palace while the ground beneath their feet is constantly stretching. At first, they can work quickly, bringing materials together faster than the ground expands. But once the stretching accelerates, their task becomes impossible. Bricks meant to connect are carried too far apart, and the grand, interconnected design can no longer be completed. This is the fate of the largest structures in our universe. The acceleration driven by dark energy acts as a cosmic brake on the growth of new giant clusters and superclusters. The vast filaments of the Webb are still stretching, and galaxies within them are being pulled ever farther apart, making new mergers across great distances increasingly rare. The most massive galaxy clusters we observe today are essentially cosmic relics, fossils from an era when gravity's pull was stronger and the universe was a more dynamic construction site. They represent the end of an age, the final monuments gravity could build before the accelerating expansion of space began to dominate. Their immense size and the hot gas within them tell the story of a more active, crowded past. Future civilizations born in galaxies now drifting apart will look out upon a far lonelier cosmos, where the great walls and clusters of our era have faded into the deepening dark, isolated islands in an ever-widening sea of expanding space. This grand cosmic story is not locked in the past. It is being actively tested and refined with every new night of observation. The narrative we have built, from quantum seeds to the accelerating Webb, is under constant scrutiny by a new generation of cosmic cartographers using telescopes of unprecedented power. These are the Great Sky Surveys, projects designed not to look at one beautiful object, but to map the heavens systematically, collecting data on millions or even billions of galaxies, stars, and other phenomena. They are our time machines and our measuring tapes, allowing us to directly observe the growth of structure across the ages. The Dark Energy Survey, for instance, meticulously charted the sky for years, using a specially built camera to measure the shapes and distances of hundreds of millions of galaxies. Its primary goal was to trace the subtle imprint of dark energy on the cosmic web, measuring how the clustering of galaxies has changed over the last several billion years. By combining observations of galaxy clustering, weak gravitational lensing, and the distances to supernova, it provided some of the tightest constraints yet on the nature of the force that now dominates cosmic evolution. But this is just the beginning. The European Space Agency's Euclid mission is now in space, embarking on a 6-year survey designed to create the largest and most accurate three-dimensional map of the universe ever made. Euclid will observe billions of galaxies out to distances of 10 billion light-years, measuring their distorted shapes with exquisite precision to map the distribution of both dark matter and dark energy. It is a mission built to answer fundamental questions. Did dark energy always behave as a simple constant, or has its strength changed over time? The answer will shape our understanding of the ultimate fate of all structure. On the ground, the Vera C. Rubin Observatory is preparing for a decade-long legacy survey of space and time, or LSST. Its enormous mirror and giant digital camera will scan the entire visible southern sky every few nights, creating a monumental cinematic record of the cosmos. It will detect billions of galaxies and track millions of transient events, from nearby asteroids to the most distant supernova. For our story of cosmic growth, Rubin will be revolutionary. It will find the faintest dwarf galaxies orbiting the Milky Way, potentially solving the missing satellites problem by revealing the ghosts of failed formation. It will trace how galaxies have merged and evolved over time by catching them in the act, and it will measure the cosmic web in such detail that the fingerprints of inflation and dark matter will be clearer than ever. And peering back to the very dawn of structure, the James Webb Space Telescope operates as our most powerful time machine. While wide-field surveys map the large-scale present, Webb stares deeply into the past, collecting the faint, reddened light from the first galaxies that ever formed. It is directly observing the era of reionization, watching as the first stellar bubbles cleared the cosmic fog. It is studying the chemistry of early galaxies, revealing how the first heavy elements from those initial stars polluted the primordial gas and enabled the next generations to form. Webb is showing us the infant versions of the cosmic web, when galaxies were smaller, more chaotic, and actively building through frequent mergers. Each of these instruments provides a different lens on the same epic story. The Rubin Observatory gives us the sprawling, high-definition present. Euclid provides the precise three-dimensional geometry of the recent past, and Webb delivers the deep, focused portrait of cosmic infancy. Together, they form an interconnected system of discovery, testing every chapter of our narrative. They measure the expansion history, weigh dark matter halos through lensing, count galaxies across time, and hunt for the faintest building blocks. With every new data release, we are not just confirming the story, we are reading the fine print, uncovering the exceptions and surprises that will lead to the next great leap in understanding. The universe's construction project is still underway, and for the first time, we have front-row seats to watch it unfold in real time. Our story of cosmic construction is remarkably successful, yet profound mysteries remain at its very foundation. We have traced the path from quantum ripples to the cosmic web, but the true nature of the two dominant forces in that story, dark matter and dark energy, continues to elude us. We know what they do, but we do not know what they are. Dark matter's gravitational pull sculpted the framework, but its particle identity is still a subject of intense search, with laboratories deep underground and in space hunting for any faint sign of interaction. Dark energy, the force now accelerating the expansion and shaping the future of all structure, is even more enigmatic. Is it a constant energy inherent to space itself, or could it be a dynamic field that has changed over the life of the universe? The answer will determine whether the cosmic web continues to stretch into isolated threads or if some other fate awaits. Beyond these giants, the detailed physics of the universe's first chapters remains tantalizingly fuzzy. How exactly did the very first stars, those immense population three giants, form from pristine gas? What were their true sizes, and how quickly did they seed the cosmos with heavy elements? The transition from those first lights to the first genuine galaxies is a frontier we are only beginning to map with observatories like the James Webb Space Telescope. Even in our advanced simulations, the messy, self-regulating feedback loops between stars, supernova, and central black holes are complex recipes we are still learning to write correctly. Getting these baryonic details right is crucial for explaining the stunning diversity of galaxies we see, from brilliant spirals to red and dead ellipticals. And looking all the way back to the beginning, we must ask, is inflation the definitive origin story for those primordial seeds? While its predictions match the cosmic microwave background with stunning accuracy, the direct, smoking gun evidence for the inflationary epoch itself remains just out of reach. Each of these open questions is a doorway to a deeper level of understanding. To walk through them, we will need new kinds of eyes on the cosmos. One of the most promising tools is the detection of the 21-centimeter line, a faint radio whisper from neutral hydrogen. This signal can act as a three-dimensional tomographic scan of the universe during the cosmic dark ages and the subsequent dawn of the first stars, revealing the precise timeline of reionization and the formation of the very first structures in unprecedented detail. Gravitational wave astronomy, listening to the ripples in spacetime from merging black holes and neutron stars, offers a completely different perspective, potentially revealing the population of the very first black holes born from those primordial stars. And in the digital realm, ever more powerful supercomputers will run next-generation simulations that seamlessly unite the vast scale of the cosmic web with the intricate astrophysics within a single galaxy, finally bridging the gap between the largest patterns and the smallest, most violent details. The journey from near-nothingness to everything we see is a narrative we have pieced together with brilliant success, but its final chapters and its deepest truths are still being written in the data of tomorrow. The universe's grandest architecture was not built from stone or steel, but from whispers and shadow. Its story is one of transformation, where the faintest possible beginnings were amplified over cosmic time into the web of galaxies we call home. It began with quantum ripples, microscopic fluctuations in the energy of space itself, stretched to cosmic proportions during a fleeting moment of inflationary expansion. These became the faint density seeds, the only blueprint the cosmos would ever need. To build from that blueprint required a hidden architect, the cold, relentless pull of dark matter. Unseen and unfelt by light, it was the first to respond to gravity's call, weaving an invisible skeleton of halos and filaments that would dictate where all luminous matter would eventually flow. Ordinary matter, the stuff of stars and planets, then played its complex and turbulent part. Flowing into those dark gravitational wells, it cooled, collapsed, and ignited, lighting up the invisible framework. Through hierarchical growth, mergers, and the explosive feedback of stars and black holes, these luminous points gathered into galaxies, which themselves were drawn along the dark matter filaments, tracing out the great walls and clusters of the cosmic web. This is how our universe constructed its greatest monuments from nearly imperceptible beginnings, a narrative written in the dual languages of gravity and light. We are not merely observers of this story, we are a part of its latest chapter. Every element in our bodies was forged in the hearts of stars that formed because of those ancient quantum seeds in galaxies shaped by dark matter halos. Our very existence is a direct consequence of this 14 billion-year construction project. As we continue to map the web with ever more powerful telescopes and simulations, we are not just learning about the distant cosmos, we are uncovering the origins of our own cosmic address. The journey from nothing to everything is still unfolding, and its next great revelations await our continued curiosity.